Welcome to my talk on durable transaction memory can scale with Timestone. This is a joint work done in collaboration with Dr. Jaeho Kim, Ajit Matthew, Shinwei, Anthony, Dr. Chang Woo Min, and Dr. Sudarshan Kannan from Rutgers University. Timestone is a highly scalable, durable transaction memory system that can be used to design crash-consistent data structures for the non-volatile main memory. Timestone is designed with three main goals in mind: high scalability, high performance, and low write amplification. At its core, Timestone has a hybrid logging mechanism called the talk logging, which is the key enabler to achieve high performance and low write amplification. In addition, Timestone adopts multi-version concurrency control for better scalability and to support multiple isolation levels. As a result of these design choices, Timestone seamlessly scales up to 112 cores and has a write amplification of less than 1, while the existing systems suffer from poor scalability and high write amplification. NVMe has finally been commercialized last year, and NVMe is great because it gives us storage-like features at the main memory speed. Like the storage, it offers data durability and it operates at magnitudes of speed greater than the traditional storage. In addition to that, NVMe also supports byte addressability like the traditional main memory, and this enables the applications to access NVMe with the common load store instructions. With the advent of NVMe, DTMs have garnered interest in both academia and the industry. DTMs are software technique that supports crash consistent updates to the main memory. As a matter of fact, guaranteeing crash consistency is one of the main prerequisites of the NVMe programming, and this makes DTMs a natural fit for the NVMe systems. Moreover, DTMs help the application developers by providing them with a generic framework to design consistent data structures. But there are some serious problems that needs to be addressed before we put the DTMs to use. In this talk, we will focus on two main problems: the poor scalability and the high write amplification. And later, we show how Timestone solves these problems. The state-of-art DTMs mostly focuses on reducing the crash consistency cost. For example, DoTM keeps the logging operations out of the critical path in order to reduce the crash consistency cost. While on the other hand, Romulus completely eliminates the need for logging by having a full backup of the original data. But unfortunately, in the course of reducing the crash consistency cost, the existing DTMs incur a very high write amplification. But before we move on, what is write amplification and why is it a serious problem? Write amplification is defined as the number of additional bytes written to the NVMe for each user requested bytes. High write amplification is always a serious problem in NVMe because NVMe has a low write endurance. And in addition to that, these additional writes generate a lot of unnecessary traffic to NVMe, which in turn causes the latency to spike up and eventually a drop in overall system performance. Apart from the write amplification problem, none of the existing DTMs considers the many core scalability in their design, which is one of the critical design principle considering the modern hardware trends. To illustrate the poor scalability, consider the following figure. This figure shows the performance of the various DTMs for a concurrent hash table with 2% update. None of the DTMs scale beyond 16 cores, even for a lower update ratio. The performance starts to drop beyond 16 cores and consistently saturates after that. Considering the fact that NVMe is going to be part of the data center scale servers, we think that multi-core scalability is inevitable for durable transaction memory systems. So, why does the existing DTMs scale so poorly? One of the main reasons for the poor scalability is the low read-write parallelism in the existing DTMs. For example, DoTM suffers from the poor scalability of the underlying software transaction memory on top of which DoTM is built. While the other systems such as Romulus or PMDK supports only single writer, which significantly affects the system performance even for a moderately higher core count. High write amplification is another scalability bottleneck in the existing durable transaction memory systems. The high write amplification stems from the large metadata overhead and the crash consistency overhead, such as the logging operations. Unfortunately, the high write amplification is incurred in the critical path of the transaction, which negatively impacts the system throughput. Considering all these problems, what we need is a durable transaction memory that has good multi-core scalability and performance and low write amplification. To address these problems, we propose the Timestone. To reiterate, the two main goals of Timestone is to achieve high scalability and performance and reduce the write amplification significantly. To achieve high scalability, Timestone needs to support better read-write parallelism. To do that, Timestone adopts multi-version concurrency control like the traditional database systems. By adopting MVCC, Timestone is able to support non-blocking reads and concurrent disjoint writes and eventually a better degree of read-write parallelism. Let me illustrate this in the following slides. Let us consider a scenario where concurrent readers are trying to read the linked list nodes. In MVCC programming model, all the readers are allowed to read the linked list nodes without requiring any synchronization. Moreover, the reads are non-blocking even in the presence of a writer inside the critical section. So, thereby by adopting MVCC, Timestone is now capable of supporting non-blocking reads. Now, let us consider a scenario where concurrent writers are trying to update the linked list nodes. Here, the writer 1 and the writer 2 are working on two different linked list nodes so that MVCC model allows both writers to proceed in the parallel without requiring any synchronization. The writers simply lock their respective nodes and proceeds with their update operation. Now, let's say the writer 2 and the writer 3 wants to update the same node. In this case, only one writer will be allowed to succeed and other will abort and retry later. By this way, Timestone is capable of supporting concurrent disjoint writes. So, now by adopting MVCC, Timestone supports a better read-write parallelism. Is that just enough to achieve the better scalability? But if we revisit the reasons for poor scalability in the existing DTMs, there are two main reasons. One, the low read-write parallelism, which the Timestone solves by adopting MVCC programming model. But we still need to address the problem of high write amplification in order to achieve a better scalability. As a matter of fact, MVCC has a potential to incur a very high write amplification as it makes out-of-place updates and maintains multiple copies of the same object. This, in fact, is contradictory to our design goal of achieving a low write amplification. To this end, we optimize MVCC specifically for the NVMM to achieve better scalability. We made two main optimization. One, we propose a novel hybrid DRAM NVMM logging scheme to reduce the write amplification. We will discuss about this logging technique in a few seconds. Also, we designed an asynchronous time-based garbage collection scheme for the log cleaning to avoid the garbage collection becoming a scalability bottleneck. To summarize the key idea for scalability, Timestone adopts MVCC to support a better read-write parallelism and optimizes MVCC specifically for NVMM in order to achieve high scalability. To achieve a low write amplification, Timestone proposes a multi-layered hybrid logging scheme called the talk logging. Talk logging includes three different logs, namely the transient version log or the T log placed in the DRAM, operation log or the O log placed in the NVMM, and lastly the checkpoint log or the C log placed in the NVMM as well. In the next slide, I will illustrate how these three logs works in tandem to reduce the write amplification in Timestone. To illustrate that, let us consider a linked list node A and a writer wanting to update it. The writer makes an out-of-place update in its private transient version log, and after the update, the writer logs the transaction semantics in its operation log, and at this point, transaction becomes durable. Before exiting, the writer sees that its T-log has reached the maximum occupancy threshold, and hence, in order to free up some space, it triggers the checkpoint operation. Note that writer checkpoints only the latest update, ignoring all the previous updates to the node A. So, this coalescing is key to achieve a low write amplification. Let's say as time progresses, there are some more checkpoints being made in the checkpoint log. In order to free up some space in the checkpoint log, the writer triggers the write back operation. And again, the writer writes back only the latest checkpoint, ignoring all the previous checkpoint made for the node A. This log coalescing becomes more significant in case of the larger data structure and especially in case of higher update ratio or a skewed workload. We illustrate the significance of log coalescing later in the evaluation section. So the key idea here is, in Timestone, we use operational logging for reducing the crash consistency overhead in the critical path. With our hybrid logging technique, we enable better log coalescing to significantly reduce the duplicate writes and the metadata overhead. To understand how Timestone works, it is important to know its object structure. Timestone is an object-based durable transaction memory. In Timestone, we store the user-defined persistent structure or the data structure in the NVMe and we call them as the master objects. To illustrate this, let us consider a simple linked list example. All the linked list nodes are stored in the NVMe and internally Timestone manages them as a master objects. Similarly, this structure can be applicable to the simple data structures such as a binary search tree or an hash table and also to the complex data structures such as a B plus tree. Next we have the version object. Each time a master object is updated, a new version object is created. All the version objects belonging to the same master objects forms the version chain. And the version chain is organized in the newest to oldest order with the latest object being stationed at the head. To understand how writes happen in Timestone, let us consider master object B and a writer wanting to update it. First, the writer makes a copy of the master object B in its tlog. Then it makes an out of place update and as a result, we get a new version object B1. After the successful update, the writer logs the semantics of transaction in its operation log. This is the durability point in Timestone and from now on, this update transaction is guaranteed to survive any crash. Now the writer then adds the new version object to the version chain by linking it to the master object B. Then the writer assigns the write clock to the new version object and this is the linearization point in the Timestone, meaning that beyond this point, any new reader or writer entering the critical section will be able to see the new version object B1. The key idea here is that any number of writers can simultaneously proceed as long as they are working on different master objects. To illustrate how read works in Timestone, let us consider a reader wanting to update master object B. Every reader will be assigned with a local clock while they enter the critical section. In this case, the local clock of our reader is 55. Now, the key question is, given that a master object can have multiple version objects, which version object a reader can dereference? The idea is that we will use local clock information in the reader and the write clock information in the version object to make this decision on which object to be dereferenced. Technically, the reader will read the first version object whose write clock is less than the local clock. Let us illustrate this. The reader checks the write clock of the first version object and in this case the write clock is greater than the local clock of the reader, which means the version object B4 is a future version with respect to this reader. The reader then skips this version and proceeds to the next version object and in this case the write clock of version object B3 is less than the reader's local clock and hence Timestone serves this reader with the version object B3. The key takeaway here is that any number of readers can simultaneously traverse the version chain without being blocked, even in case of an ongoing write. There are many other interesting features in Timestone that we did not cover in this talk in the interest of time. Please refer to the paper for the more details. By evaluating Timestone, we wanted to answer the following questions. What is the write amplification in Timestone? Is the log coalescing beneficial in reducing the write amplification as we illustrated previously? And does the Timestone scale as expected? And finally, what is the impact of Timestone on the real world workload? We evaluate Timestone on the real NVMe server with 1 terabyte capacity and 112 logical cores. We use a variety of benchmarks to evaluate Timestone and compare them against the state-of-art DTM systems. In this figure, we show the write amplification of different DTM systems for a write-intensive hash table. As shown, Timestone consistently maintains write amplification less than 1, while the other DTMs such as do-TM incurs a write amplification of up to 6x and Romulus up to 2x consistently. The lower write amplification in Timestone can be attributed to the low overhead operation logging in the critical path and a better log coalescing, which I will illustrate shortly. Also, the PMDK incurs a high write amplification of up to 70x even for a 2% update case, and hence we did not show the numbers of PMDK in this figure. In our paper, we describe the breakdown of write amplification in PMDK in a detailed manner. To support the low write amplification in Timestone, we present the amount of writes incurred in each of the logs in Timestone. If we see closely, only 7% of the writes are being checkpointed to the C log from the transient log, the rest being coalesced in the transient log itself. Similarly, only a fraction of T log writes are eventually written back to the master object, meaning that a huge amount of writes are being coalesced in the T log and the C log itself. So this eventually answers our question on why write amplification in Timestone is consistently less than 1 and when compared to the other systems. Next, we present the scalability results of Timestone. In this figure, we illustrate the scalability of Timestone for a concurrent hash table with 2% update. As shown, Timestone scales linearly while the other DTMs does not scale beyond 16 cores. Also, Timestone performs up to 70 times better than the Romulus, which is the next best performing DTM system. Further, we show the scalability of Timestone for a write intensive workload, and this figure represents the performance and scalability of Timestone for a concurrent hash table with 80% update. Still, the Timestone is able to scale linearly and it performs 100 times better than the do-TM, which is the next best performing DTM system. To summarize, Timestone supports better read-write parallelism than the existing DTMs and hence it shows superior scalability. The lower write amplification in Timestone makes the critical path shorter, which eventually leads to a better performance and high scalability. In the paper, we also show the scalability results for linked list, binary search tree and B+tree as well. To study the impact of Timestone on the real-world application, we use the Kyoto cabinet, which is an in-memory database system. We replace the original binary search tree in the Kyoto cabinet with the Timestone-enabled binary search tree to provide crash consistency to the database operations. We compare the performance with the vanilla Kyoto cabinet running on the DRAM and also with the vanilla Kyoto cabinet that runs on the NVMe. As shown, Timestone scales well and performs up to 3 times better than the vanilla Kyoto cabinet that is running on the faster DRAM. Also, Timestone-enabled Kyoto cabinet guarantees crash consistency, while none of the other systems that we compare with does that. And still, Timestone is able to perform and scale better than its counterparts. As we come to the end of this talk, we would like to thank and appreciate all the previous work on the DTM systems. To name a few, Romulus, do-TM, PMDK, Mnemosyne, etc. The use of MVCC for the main memory in Timestone is inspired from in-memory database systems like Cicada and Hermia. Then we adapted the MVCC and optimized it for NVMe to achieve better scalability and performance. Also, our work is inspired from the non-linearizable synchronization algorithms like the RCU, RLU and our own work MVRLU. So now the Timestone gives us good scalability, good performance. Then one of the future direction that we can think of is providing Timestone with the memory safety and reliability. Timestone operates entirely in the user space and it is important to guarantee reliability for the application that uses Timestone. And another interesting direction that we can think of is to extending Timestone to support distributed transactions. To conclude, current DTMs do not scale beyond 16 cores and they suffer from high write amplification problem. So we propose Timestone to address these problems, and Timestone adapts MVCC to support better read-write parallelism and proposes talk logging to reduce the write amplification. As a result, Timestone scales up to 112 cores for a different variety of workloads and data structure, and it performs up to 100 times better than the state-of-art DTMs. Thank you for taking time to listen to my talk, and we authors are happy to answer any question through the dedicated Slack channel or via email. Thank you.